So I'm going to walk through two examples of hypothesis tests for a proportion here. And in each one, I'm going to use both methods. I'm going to use both the p-value method and the critical value method so that you can see each one of them in action. All right, so you see here we have kind of a manufacturing example. The M&M Mars people have a claim about the proportion of each color, right, that shows up in a bag of M&Ms. And specifically, they would like us to believe that 13% of any given bag is going to be brown, right? So that's going to be our claim, right? The claim is always what it is we're asserting. So the claim will be the proportion of brown M&Ms is 0.13. Okay, so building off of that, right? Remember, the null hypothesis always has equals in it, right? So my null hypothesis is going to be P is equal to 0.13. Now it's the alternative hypothesis where we have choices. Do we want to do greater than, less than, or not equal to? Well, what are we trying to test here? If it's over, that's going to be bad because they're wrong. And if it's going to be under, that's also bad, for different reasons, but both of those results would be considered unacceptable, right? So we're going to be using as our alternative hypothesis, P is not equal to 0.13. And that's key right there because that immediately tells me I'm going to be doing a two-tailed test, right? Not equals is always two-tailed. All right, so how about the significance level? We're also given that in the question. Alpha is 0.05, right? So let's do a quick picture. You know, I love to draw, get a good picture going here, right? So we're doing a two-tailed test, right? So we want the total in both of the tails to be 0.05. That means each individual tail is going to have half that, or 0.025. Okay, good. So I need to calculate. I'm going to do the p-value method first, right? So I'll make a note here. We're doing the p-value method. So to do that, what I need to do is I need to calculate the probability that the results that I'm seeing in my sample occurred compared to this accepted value of 0.13. All right, so what is my p hat value? Remember, that is always the proportion that came from the sample. Right, so in a sample of 100 M&Ms, I'm seeing 8 that are brown. So this will be 8 out of 100, or 0.08. Okay, so what I want to know is, what is the probability of getting that result, assuming that 0.13 really is the correct value? All right, well, to do that, I need a z-score. This is my test statistic, right? That's a z-score. Remember, the formula here is excuse me, p hat minus p divided by the square root of pq over n. And if you take our numbers, right, let's put some numbers in here. This is 0.08 minus 0.13 over the square root 0.13. Q is 1 minus p, right? So that's 0.87 over 100. And that is negative 1.49. Okay, so what is the area outside plus or minus 1.49? Right, so I want P absolute value of Z greater than 1.49. And that's two numbers, right? It's the probability that Z is less than negative 1.49 plus the probability that Z is greater than 1.49. Now you're going to your table, right? Each of these individual probabilities is 0.0681. And if we double that, this is 0.1362. That is my p-value, right? Remember to use the p-value method. This is a probability. This significance level, that's a probability. We compare the two, right? My p-value is greater than alpha. So remember, when the p-value is greater than alpha, what this is saying is the likelihood that what I'm seeing occurred just by random chance is pretty high. Specifically, it's higher than my tolerance level, right? So this means, and I'm going to be very specific in my language here, we fail to reject the null hypothesis. There is no evidence that would cause me to reject it. Now, remember, we're not done. Okay, kind of the statistics part is done, yeah. But we always need to state our final conclusion in plain English, like you're going into a meeting of the board of directors and you had to give them an answer to this question. They don't want to hear about a null hypothesis, right? They want the final conclusion to be stated in terms of the claim. Okay, so here's how I think this through in my head. And I'm going to use some language that is technically not the correct statistical language, but it works to help me think this through in plain English, right? We fail to reject the null hypothesis, right? In other words, I like the null hypothesis. Okay, I like very non-technical phrase, okay? But it gets the idea across. I like the null hypothesis, and because the null hypothesis is the same as the claim, I like the claim, right? So, in other words, we fail to reject the null hypothesis that 13% of the M&Ms are brown, which means, again, in terms of the claim, in plain English, there is no evidence to assume that M&M Mars is incorrect in claiming that 13% of the M&Ms in a bag are brown. Okay, so that's the p-value method, right? That's the p-value method. You notice what I did here, right? I found this z-score, and I found the area outside of it, and I found that that area is greater than, I don't know where the z-score is, we're actually going to find this in a minute, right? Or the critical value. I found this number, and this area was greater than my limit. Okay, that's how the p-value works. It's based on comparing probabilities. Right, now let's shut this down. I'm just going to clean up here because I need the space. And we will do this again, this time using the critical value. The critical value method. Sorry, give me just another second here, and I'll have everything cleaned up. And I'm even going to restart my diagram, because I think the diagram helps here. Okay, so let's look at the diagram. Right, here's our picture. And we're kind of starting from the same place, right? I have these numbers here. And I know that I want 0.025 in each tail. Okay, so here's how the critical value method works. I need to know what these z-scores are. What z-score gives me 0.025 in each of the tails? Well, you go to your table, right? This is 1.96, and this is negative 1.96, right? And then you remember, I won't go through calculating it again, but you remember our test statistic was negative 0.49. Make a note, critical value method is what we're doing now. Where is that test statistic? Right, if I go to graph this, negative 1.49 is right here, and positive 1.49 would be right here, right? So the test statistic is inside of those two boundaries, right? And when we're doing the critical value method, that is the criteria that will lead us to the same conclusion, to reject the null hypothesis. To say there is insufficient evidence to reject the null hypothesis that 13% of the M&Ms are brown. In other words, there is evidence to support the claim made by M&M Mars. We think there, and I always try to stop myself because I try a little to be too plain English sometimes. There is evidence to support the claim that the number of brown M&Ms is 13%, right? That would be the language. So let's try another one. And if you like, you can pause, right? If you like, to see if you can work through this on your own. Then start it up again and we'll go through it together. All right, so now we're talking about a medical test. And I'm going to follow the same process, right? First, I need to state the claim, right? And this is usually pretty explicitly stated in the question. And it says here in the last sentence, test the claim that the new drug has a better performance than the old one. Well, the old one's performance was 76%. I'm claiming that we can do better than that. So my claim is performance is better than 76%. Okay. So, what's my null hypothesis? Well, again, I'm talking about a percentage, right? So we're still talking about proportions. So I'm going to say P is equal to 0.76. Null hypothesis always has equals. And my alternative hypothesis is going to be P is greater than 0.76. Right? If it's less than, I care, right? Because that would be bad for us. But what I'm interested in is showing that we can do better, right? We can get a higher success rate. All right, so our significance level, alpha, is going to be, let's use 0.01. That's pretty common in medical tests, right? They like to have a high level of confidence in their final result. All right, and again, I'm going to draw a quick sketch. Right, we're doing a single tail test, right, because I have just one inequality here. And because I'm looking for greater than 0.76, I'm going to be doing a right-tailed test. Okay. Let's see, what is P hat here? What are we getting from our sample? And our sample, 16 of 20 patients recovered. That's 0.80, which is higher, Well, it's good. I mean, we got a better result. Is it better enough? Right, that's what we're trying to test here. All right, so Z is my test statistic. Same formula, P hat minus P square root of PQ over N. So let's see, 0.8 minus 0.76 square root of, let's see, 0.76 times 0.24 over 20. And my calculator tells me this is 0.4189. Okay, so now doing p-value method here first. What is the probability that Z is greater than 0.4189? You go to your table, whatever method you like to use to do this. This is 0.337645, which is greater than alpha. All right, so this means that the likelihood that the difference we're seeing between the sample and the current success rate has a high probability of being just random chance. Therefore, there is insufficient evidence to reject the null hypothesis. Now here, our final statement is going to be different, right? Our null hypothesis, which we like, this is kind of my informal phrasing, the null hypothesis which we like is different from the claim, right? So because we like the null hypothesis, we don't like the claim. So what I would say is there is insufficient evidence to support the claim that the success rate of the new drug is better than the existing 76%. Okay, that's the p-value method. How about the critical value method? For the critical value method, I need to know what is the z-score of this point, right? What z-score has 0.01 to the right of it? Well, if you go to your table, this is 2.326, or Excel, your calculator, whatever you're using there. That z-score, so where is our test statistic? Right, our test statistic is a poor, lowly 0.4189. That's all the way over here. So it is not out there in the critical region, right? So we get the same conclusion, right? Both methods are giving us the same result. There is insufficient evidence to support the claim that this drug is doing better than the previous one. Okay, so that's a test for proportion, right? In the next lecture, we're going to do very similar. We're going to really follow the exact same thought process, right? Very similar, only we're going to do tests involving a mean rather than a proportion.